The resonant frequency, often called the natural frequency, is a special frequency for a system, such that when a system is driven at this natural frequency, or are multiple, or as we call it, a harmonic of this frequency, a standing wave forms, and this often means special things happen. This can also happen when a system receives an impulse of energy and is allowed to relax to its natural frequency, or one of its higher harmonics. This idea of resonant frequency spans many branches of physics, and you see it in cello strings, pipe organs, and saxophones. But it's also present in more destructive phenomena, such as when a glass shatters, or when wind hits a bridge with just the right speed and frequency to cause it to oscillate with ever-grading amplitude to finally crash. A key parameter of any resonant circuit is its quality factor. This quality factor being defined as the energy stored divided by the energy dissipated per unit cycle or time cycle. It originated from the damped driven oscillator, with beta being the damping constant. And when looking at resonant signals, they often have a shape like this, though sometimes they can be upside down like this. They are fitted with what's called a Lorentzian, or a circle fit, as you see on the screen. A defining feature of the quality factor is its full width half maximum, which is the full width of the curve at half of its maximum height. The skinnier it is, the higher the quality factor, with the skinniest and sharpest curves coming from superconducting circuits because of their extremely low loss. These high Q circuits can be fabricated in a clean room using lithographic techniques, essentially removing parts of the metal that we don't want to create a circuit pattern, the simplest being a coplanar waveguide, which is just a single transmission line surrounded by a trench on either side, and then from there ground planes on either side. You can see an example on the screen. Here we have a picture of a coplanar waveguide. On either side you see a coupled quarter wave resonator. You can see that each of these are different lengths. Some of them are curved inwards. This is because these are each of these are resonating cavities whose resonating frequency depends on the length of that cavity. Now these quarter wave resonators are capacitively coupled to our transmission line, meaning they interact through the electric field. Here's a good explanation via acoustics of how coupling works.
These two tuning forks which are on the same frequency, 256. If I sound one of them, the sound gets transported to the other through resonance, and back again.
So you can think of coupling as an energy transfer through resonance. Here you can see with these quarter wave multiplex resonating cavities that they are coupled to our main transmission line, the thick transmission line, via a capacitive coupling. They are talking via the electric field. Here is another example of a different line using aluminum oxide that are also capacitively coupled. The important thing to note is that there is no touching, that they are separated by a distance. The smaller this distance, the stronger the coupling. Here's an example of an inductive coupled device. Though this device is a lumped element device that's bias tunable, meaning you can put your own bias of DC current to change the resonance frequency. This itself is its own subject in its own. But it's an example of a resonating element that's on these types of devices. Resemble of a kinetic inductance detector. Now just because these are high Q devices doesn't mean they always work. Here is a defect that's about a quarter of the size of a human hair that caused my device to stop working completely. CPWs are simple devices, but they have a variety of uses. One, like you see here, is you can measure the dielectric properties of materials deposited on top. Here's a picture of that same chip mounted in its sample holder. You need a microscope to put the connections. Sometimes the cavity itself is the means of information transportation. Here you can see what is called a Josephson junction mounted into a 3D cavity. This Josephson junction is the nonlinear element which provides the heart of a qubit, and it couples capacitively with the 3D cavity. Essentially, we can read the state of the qubit by reading the state of the cavity. A way to indicate if your qubit is indeed coupled to your cavity is to do a small measurement than a strong measurement. And if there's a shift in resonant frequency of the resonant cavity, then we know that the qubit has strongly coupled to the resonant cavity, as the strength of the coupling is proportional to the signal strength. Now, an interesting thing with this qubit setup is its resistance to charge noise. Because of that, we can measure this qubit in a fridge not traditionally set up for qubit measurement. And here you can see a typical signal given from that, something called the T2 coherence time. It's a very noisy signal, but we got it.